Hello and welcome to the R Help session for February 16th. This is Jared speaking, and you'll see that I've opened the file here that we'll work through, and specifically we're covering functions you'll need for your homework assignment that is due Sunday, February 18th. You may also notice that my RStudio layout is a bit different than yours. Instead of having both the script and the console on the left side, I've moved the script over to the right and move the environment and some of the other tabs to the bottom left. I find this is easier to see more of my script, which is what I usually want to be seeing. And you can do this simply by going to View, Panes, Pane Layout. And from here you can choose where each of these pieces ends up in your quadrants. Okay? That is totally unnecessary to do, and it's simply something to do if you find it's helpful. So we're going to start out with a suggestion from the homework. Your homework assignments usually suggest that you run this line of code to increase the number of significant digits in your answers to 10. So now, let's say you type in 1/3, we're going to get 10 decimal digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, easy enough. So some useful tips. Oftentimes you'll see number colon another number. This gives you a sequence of integers from 0 to 6. Similarly, you could do 1 to 100, and it's just an easy way to get a list of numbers. Next, we have our square root function. It's just sqrt. Square root of 4 is 2, and that we know. All right, so those are two things that we'll have to see and come back to later. The two things we wanted to review so that we can come back to them later. Hopefully in 309 you recall the use of pnorm. If your class was in R, if your class was not in R, we're going to review that now. If you don't know what pnorm is, or anything is in R for that matter, simply run $name. So in this case it's $pnorm. And here on our help page, we know all about the normal distribution. The normal distribution has 4 different functions: dnorm, pnorm, qnorm, and rnorm. The one we're focusing on today is pnorm. Notice here pnorm takes a value, which it calls q, as well as a mean and a standard deviation to establish which normal distribution it is. And these last two arguments you can ignore for now, but basically, because pnorm gives you the probability to the left of point q, that's also the lower tail of our bell curve. You can ask for the lower tail equal true, which is by default. Each of these equal signs means this is the default. And if it's equal to false, then you'll be looking at the upper tail instead. And you can also get back the log normal answer, but we're not worrying about that today. Or for a little while at least. So if I ask for the pnorm of 2, given mean 0, standard deviation 1, this is equal to the probability that x is less than 2 if x was a normal variable with mean 0 and standard deviation 1. We get 0.977 as the integral from negative infinity to 2 of that normal distribution. Note, though, that the mean and standard deviation by default are already 0 and 1, and you can simply run pnorm of 2 and get the same answer. Pnorm is used to find probabilities of x, or whatever your variable is, being less than a value. That value is this q. Okay? Next, we'll look at how to get sample statistics from a vector. So data is usually stored in vectors or matrices or data frames, which is just a fancy matrix. In this case, my vector is going to be all the digits from 1 to 100. Remember that colon operator. I can take the mean of all numbers 1 to 100, and I get about 50, which you would expect. I can get the variance of that vector. I can also get the standard deviation of that vector. So mean gives you the average, var gives you the variance, SD gives you the standard deviation. What will happen if I take that standard deviation and square it? By definition, I should get back to the variance. Yep, 841, 841. Remember though that these are all this is the sample variance and the sample standard deviation. So we've called this in the past S, or perhaps sigma hat. It's an estimate using your data of the actual standard deviation. So we call it the sample standard deviation. It's not the population standard deviation. The last test we want to talk about, the last function we want to talk about in detail is t.test. As you may guess, this is how to perform a t-test in R. Let's look at its help page. t.test takes a vector, x, which we see here is described as a non-empty numeric vector of data values. So in our case, we can use that on 1 through 10. Let's see what happens if we run this on 1 through 10. Scroll this down a bit so we can see. All right, we did a one sample t-test using the data of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the data. What is this testing, or t-testing what? By default, we're assuming the true mean, mu, is equal to 0. Remember the default's down here. Our alternative and our alternative hypothesis is two-sided. So hence here we have that the alternative hypothesis is the true mean not equal to 0. Remember, not equal to is the giveaway that this is a two-sided p-value. Calculates the t-statistic, which is just the x bar minus mu divided by s over root n. Hopefully that sounds at least a little bit familiar from Stat 309. And it comes back and we get a p-value of 0.00278. 0.00278. This is so small, we can't help but think that the true mean of whatever process generated this data is non-zero. Well, it seems a little silly to test this as 0 because we know that these are integers between 1 and 10. So what if we test that the true mean is equal to 5? We now specify an option, mu equal 5. And we have the same data, same degrees of freedom, except now our alternative hypothesis is that the true mean is not equal to 5. And you see that the p-value is huge because our mean is very close to the value of 5, which might be the true mean. Let's say we're only interested in the greater than version. What if we want to know the probability that our data has a true mean of greater than 5? We now specify I should correct myself, because you have to interpret p-values very carefully. Given that the null hypothesis is true, we were curious about the probability of finding a response like ours, or more extreme, or in this case, greater than. So our alternative hypothesis now is that the true mean is greater than 5, for which we have a p-value that's still not significant, which makes sense because 5.5 is not that different than 5, especially when you get numbers like 1 and 10 involved. Okay, so these were all one sample t-tests where we can change the hypothesized value of mu as well as the direction of our alternative hypothesis. Similarly, you could put less than or two-sided, which it says right here. Last but not least, we can do a two-sample t-test. We take our group 1, which is 1 through 10, take our group 2, which is going to be 4 through 16, and we'll do a two-sample t-test between them. All right, so remember, we didn't specify mu or the alternative, so mu is going to be 0. In other words, the difference between group 1 and 2, if the null hypothesis is true, is 0. There's no difference. We didn't specify an alternative, so our alternative hypothesis is just that the true difference in means is not equal to 0. And we see this is a very small p-value, which is evidence against the alternative hypothesis. Also notice that one of the things that comes out of here every time we run this t.test is a 95% confidence interval. Here we already have a 95% confidence interval for the difference between group 1's and group 2's means. In other words, mu1 and mu2. That difference is somewhere between negative 7.5 and negative 1.5 with 95% confidence. What if you wanted a 90% confidence interval? Here we can get for one sample, just group 1, we can get a 90% confidence interval about the mean. And we're 90% confident that the mean of these integers, the true mean of this integer set, is between 3.7 and 7.25, or 7.3 if we round. That's all the material for today, and this should introduce all the functions you need to successfully complete your homework. I hope you have a great weekend.